When light passes through a prism, it does three things. The three Ds: dispersion, deviation, and displacement. Dispersion is when white light goes through a prism and the prism breaks it out into its spectral colors, which are Roy G. Bibb: red, orange, yellow, green, blue, indigo, violet. When a light ray goes through a prism, it is deviated from the path that it was on and bent or deviated towards the base of the prism. Okay, that's deviation. Okay, this takes just a little bit of imagination. It's not really difficult to understand. It's a little bit difficult to explain. So I'm going to try here. Hope it works. Okay, imagine looking at something across the room at the wall that is above your head. Like you have to tilt your chin up a little bit in a straight gaze across the room towards the wall. Okay, that's sort of what this eye is doing. You see from the eye a line of sight. It's solid and then it's dotted to show where this person is still gazing in that direction. Now the light is deviated, okay? And what this person is seeing, because of the way the light bends, is something that's like down on the ground. So they're looking above their head, but they're seeing an object that is actually on the ground, okay? That's called displacement. The object is on the ground, but the image is displaced towards the apex of the prism. It is a virtual image. Okay, so light deviates towards the base, images are displaced towards the apex. Okay, the apical angle is of course the angle of the apex of the prism, and it's shown here in the dark orange color. And the deviating angle is the angle formed by, imagine if the light ray that's coming, the incident ray, the one that's coming into the prism, were to continue on and not be deviated, and the angle formed between that and the actual deviation of the light ray is the angle of deviation. I hope that makes sense. And then there's a formula for the angle of deviation to determine what it is, and it is the angle of deviation equals the apical angle times the difference in refractive indices. Okay, one is the refractive index of air, which we're assuming is surrounding this prism, and n is the refractive index of the prism, whether it's glass or plastic or what have you. Okay, so n minus 1 is just the difference in refractive indices. Okay, I don't think that it's important to memorize this formula, and I'm not going to work out any problems using this formula, but what is important is to understand what the formula means. Okay, so let's think about it a second. This is saying the angle of deviation, which means how much the light is bent by the prism, is dependent upon the apical angle. So if it's a narrower angle or a wider angle, think of what that's going to do to the shape of the prism. It depends upon that, and it depends upon the material that the prism is made out of. Now, clinically, I'm pretty sure that you're not going to see any glass prism. It's just not very common. Almost all prisms in a clinic are made out of plastic now. But this formula is telling us that the same size glass prism and plastic prism, everything else being equal, but different materials, are going to deviate the light differently. And it's also telling us, regardless of the material, that the shape of the prism, the apical angle, whether it's wide or narrow, is going to have an effect on how the light is deviated. Maybe I should try to write that out in words. Okay, that was the angle of deviation. Remember, that's the light ray. And this is the displacement of the image, okay? This is the formula for that. And that is actually what a prism diopter is. A prism diopter is how much it displaces that image, see that cat, how much it displaces that image or object. And as I said, this is a formula that really defines what a prism diopter is. What it says is one prism diopter produces 1 centimeter of displacement at an object distance of 1 meter. And you really need to know that. And you need to know the basic formula too to figure out, if you're given different distances, if you're given different diopters, what the displacement would be and such. And we'll do a couple problems with that. I think this needs a picture. Okay, so I have this prism and I have a cat that's sitting exactly 1 meter from the prism. And I'm going to look through the prism, and when I do, I will see the cat displaced 1 centimeter towards the apex of the prism. What does this mean? This means that the strength of my prism is 1 prism diopter. Now, don't criticize my proportions. I'm well aware that compared to the meter that I drew, that does not look like 1 centimeter. My proportions are never right in these videos. I know that, but that's not the point of the picture, so let's do some problems. Okay, first problem. I would like to displace an object that is 1 meter away from me, a distance of 6 centimeters. What strength prism would I need? Okay, first let's define our variables. P is a variable that stands for prism diopters. I am using DISP for displacement and DIST for object distance. And I just kind of made those up, pulled them out of air somewhere, but I think they fit. And what we're looking for in this problem is P. We don't know that. The displacement it gives us is we want to displace an object 6 centimeters, and that object distance is 1 meter. And then all we have to do is plug the numbers into the formula and solve, and we come out with 6 prism diopters is the strength of prism that we would need to displace an object that's 1 meter away by 6 centimeters. Okay, we'll just do one more. How much would a 7 diopter prism displace an object that is 3 meters away? All right, what do we know and what don't we know? We know that the prism diopter power is 7 diopters, 7 prism diopters. We know that the distance away is 3 meters, and we need to know the displacement. Okay, we just fill the numbers into the formula, and then we will multiply both sides by 3 to get rid of that 3 in the denominator, and we end up with an answer of 21 centimeters. Okay, so you see that the math here is simple. The effort comes in memorizing the formula. Now, I wrote the formula in 2 different formats up at the top. I would suggest memorizing the one on the right at the top, the 1 prism diopter equals 1 centimeter over 1 meter. I would suggest 1, understanding what it means, 2, being able to memorize it like in sentence form, and then 3, being able to memorize it in formula form. Okay, and sentence form would be something like the strength of 1 prism diopter will displace an object 1 meter away by 1 centimeter. Okay, or however you want to phrase the sentence, memorize it that way. understand what it means, and then be able to write it in formula format. That's my suggestion. When you want to add prism together to compound the effect of the prisms, or let's say you want to divide out the total amount of prism between the two eyes. Let's say you want to prescribe 6 diopters of prism. Generally, it's best to divide that amount of prism between both eyes. I'm not going to go into that quite yet, but it's a lot of prism and it's best to divide it. So for 6 diopters, you would probably choose 3 per eye. And yes, you can do that, but it's very important to orient each prism in each eye in the proper direction, or they could end up canceling the effects of one another instead of compounding the effects. Okay, in order for me to explain this easily, I want you to think about it in 2 different ways, compounding horizontally and compounding vertically, because they're done differently, okay? By horizontally, I mean base in or base out, okay? By vertically, I mean base up or base down. Okay, I want to prescribe Prism for this patient here who has an esotropia, a left esotropia, okay? First I'm going to place 3 diopters over the left eye, and then I'm going to place the other 3 diopters over the right eye. This is the one we're doing the 6 diopters, okay? When you're placing horizontal prism, it's pointed in the direction that the eye is pointed, okay? So for this ESO, the eye is pointed in towards the nose, so the prism is going to be pointed in towards the nose. And what I mean by that is, when I say pointed, I mean the pointy and the apex, okay? It's called base out, but I think it's easier to remember that the prism points in the direction of the eye, the deviation. And when you're splitting it and you're placing some of the prism over the fixed eye, the one that's straight ahead, that's not deviated, you're going to do the same thing. If it's an ESO deviation and you're pointing it in towards the nose, you're going to point both in towards the nose to compound. Okay, now I got some big eyes. Okay, for a vertical deviation, you're also going to point the prism in the direction of the eye, but if you're placing some over the fixed eye as well, you're going to place it in the opposite direction. So in this case, I have a right hyperdeviation, a right hypertropia. I'm going to place the prism base down in the deviated eye, and in the fixed eye, I'm going to place the prism base up, and that would be compounding in the vertical prisms. Okay, so it's different than in the horizontal. Okay, the orientation of the prism in these next few slides show 2 prisms canceling one another out. This patient is not getting the effects of prism because they're placed in the wrong direction to compound one another. They're simply canceling the effects of one another. Okay, here's another question. Why do we place prism in the same direction in each eye for compounding horizontally, in different directions in each eye for compounding vertically? Well, the answer to that is kind of we don't. We just call them same and different. Watch. Okay, these are some of the more important points that we've just gone over. Okay, displacement refers to the image or the object. Technically the image, but object sort of. Deviation refers to a light ray. Okay, images and objects are displaced. Images of objects are displaced, let's say that. For deviation, light rays are deviated. Okay. Light traveling through a prism will be bent towards the base. Definitely remember that. The image will be shifted towards the apex. Okay. And one prism diopter produces 1 centimeter of displacement at an object distance of 1 meter. That's the formula right underneath it. Remember that. And Prentice's law, okay, which is prism diopters equals the distance from the optical center in centimeters times the dioptric power of the lens. And we haven't talked about that, so let's talk about that right now. Okay, spherical lenses can be thought of as 2 prisms put together. For a convex lens, it's 2 prisms base to base, and for a concave lens, it would be 2 prisms apex to apex. Okay, now we have a patient on the far left of the screen and one on the far right of the screen. And each of these is looking through a lens right at the optical center. Okay, remember in the convex lens, the optical center is the thickest point right in the center of the thickest point on the lens. And for a concave, it's the very thinnest point on the lens. Okay. And because they're both looking through the optical centers, there is no image displacement. Okay, now we're going to slide both of these lenses down so that these patients are no longer looking through the optical centers of the lens. Now they're looking through some point of a prism. We'll do one at a time here. The patient on the left, you can see that the light has deviated towards the base, and that caused the image to be displaced towards the apex. So this is actually what happens when you or a patient or anyone is looking through a convex lens and not looking through the optical center of the lens. Something to keep in mind when you see your patients and their glasses are all askew. Now in the concave lens, of course, the image is displaced in the opposite direction as the convex lens. So the light is deviated towards the base, and the image is displaced towards the apex. So it's kind of interesting. We'll see them both together. Once again, both of these lenses were moved down, and the image of the object was displaced towards the apex of the prism. The image through the convex lens was displaced upwards, and the image through the concave lens was displaced downwards. Okay, there's a term for each of these shifts. For the convex lens, the motion up is called against motion or against movement. With the concave lens, it's called with motion or with movement. So, if you're looking at a pair of glasses, in this picture, the blue dot represents the optical center of the lens. And remember, in a convex lens, that's the very thickest part, and in a concave lens, that's the very thinnest part. And the red X's are the patient's visual axis, the optical axis of the patient. If those coincide, if those are in line, then there's no prism. There's no prismatic effect. There's no induced prism, accidentally or intended. If the optical center of the lens, either on one lens or both lenses, if an optical center is nasal to the patient's visual axis, that's called inward decentration. If the optical center is temporal to the patient's optical axis, it's called outward decentration. And then, of course, we have superior decentration and inferior decentration. Okay, so here's a question. How much prism? Okay, let's take this inferior decentration. How much prism is being induced, whether accidentally or intentionally? What is the effective prism if the optical centers were decentered inferiorly? Well, think about it for a second. That's going to depend on a lot of things. It's going to depend on whether it's a convex or concave lens. It's going to depend on the power of the lens, how strong it is. And it's going to depend on how much. How much is the decentration? Okay. There's a formula for this. And it says that the prism diopters, in other words, the effective prism, would be equal to the distance from the optical center in centimeters. Now, you're usually given distance from the optical center in millimeters because it's going to be small, but in the formula you have to convert it to centimeters. The distance from the optical center in centimeters times the power of the lenses. You probably want to memorize this formula. Okay, I threw in here a couple of problems to figure out. Now you can either figure them out with me, or you can read the problem, pause it, try your hand at it yourself, and then check your answer. Okay? The next few problems all came from the Certified Ophthalmic Technician Exam Review Manual by Janice K. Ledford. Okay? So the first one is, a plus 4.25 sphere is decentered in by 0.5 centimeters. What is the prismatic effect? What I would recommend doing first is defining your variables, knowing what you're trying to find. Okay, so P, we don't know. That's what we're looking for. C is 0.5 centimeters. And D is plus 4.25 diopters. So we just plug in our numbers and solve, and we get 2.125 prism diopters. Now, which way? What is the prismatic effect? Is it base in, base out, base up, base down? We know it's 2.125. I highly, strongly, greatly recommend drawing a picture and following your picture all the way through. I can't stress that enough, because if you're taking the certification exam, you're going to have a multiple choice, an A, B, C, and D to choose from. You might get this far, but I guarantee you're going to have two answers. You're going to have a 2.125 prism diopters base in, or a 2.125 prism diopters base out. And if you don't know the base in or the base out, then you're going to get the wrong answer. You might as well not even have bothered doing this part. Okay? And it's tricky. Draw a picture. So drawing a picture, the first thing you want to know, is it a plus lens or a minus lens? In this case, it's a plus lens. So we're going to put two prisms base to base for each lens. Okay? That's what we do for the plus lens. For the minus lens, it looks more like a bow tie. Okay, the optical centers of each of these lenses are right where base meets base. That's the optical center. So if the patient's visual axis in the red X were right there at the optical center, there would be no prismatic effect. But we're moving the optical centers in, which means nasal. That leaves the patient looking through a prism that is base in. Okay, next question. The patient requires a minus 650 spherical correction and a 3 prism diopters base up in the right eye. How much should the lens be decentered, and in which direction? So we're intentionally decentering here. This is intended prism. Answer A, B, C, and D. So we have 3 prism diopters. We don't know the decentration. and we have a minus 650 diopter power lens. So we just plugged in the numbers, solved for C, and then we switched it to millimeters because that's what the answer is in. Now, to draw the picture. Well, it's a minus lens, so our lens is going to be shaped more like a bow tie. But our problem says base up, so we're talking about vertical prism rather than horizontal. So we're not going to do the bow tie, we're going to put it on its end more like an hourglass. Okay, I'm going to bring our selection of answers back up because we can narrow down a little bit at this point. We have figured out that we need a decentration of 4.6 millimeters, so we're not looking at A or B anymore, just C and D. I feel like this is one of those problems where you have to take your time and read it carefully and be certain of what they're asking. I circled optical axis here because the optical axis, remember, is the patient's line of sight. It has nothing to do really with the eyeglass lenses. We're talking about the person, not the lenses. Okay? So we're going to draw in the optical axis right at the optic center of these lenses, and then we'll decide what to do with the right lens to induce prism. So we want base up prism in the right lens, so we're just going to slide the right lens down. That'll give us base up prism, right? So which direction is that right lens decentered? Is it below the optical axis or above the optical axis? We're talking about the optical center of the lens, and it is below the optical axis now. The answer is A. Okay, let's try this problem. The patient is wearing a plus 2.75 sphere in the right eye and a plus 2 sphere in the left eye. The lenses are decentered in by 2.75 millimeters in the right eye and 1.25 millimeters in the left eye. What is the approximate total prismatic effect? Okay, my first thought is, are we compounding or are we canceling? Because that's something really important to check when you get a problem like this. What is the approximate total prismatic effect? You want to make sure that the prisms are placed in such a way that they're not canceling. If they are, then you subtract what you get in each eye. If they're compounding, of course, you're going to add the effects from each eye. So let's reread the problem here and see that both are decentered in. So we're talking horizontal, both in, so we're compounding. So we can figure out the prismatic effect for each eye and then just add them together for the total. Okay, so we'll start with figuring out the right eye, and we'll define our variables. We're looking for the prismatic effect, so we're looking for P, we don't know P. C, the lenses are decentered in by 2.75 millimeters. We want C in centimeters, so instead of 2.75, we're going to put 0.275. And then the right lens power is plus 2.75 diopters. Then we just plug the numbers into the formula and solve. And we find that the patient has a 0.7562 prism diopters in the right eye. Let's figure out what's in the left eye. And we get a 0.25 prism diopters in the left eye. What do we do now? We said it before. Just add them together to find the approximate total effect. The total effect is 1 prism diopter. Which way? What do we do next? Draw a picture. So I'm going to clear some space so we can draw a picture here. Now, I always start out, when I draw it, I start out drawing the optical axis right at the optical centers of the lenses. Then I move them either the way I'm told to in the problem or the way that I need to figure out the problem. So here they are right at the optical centers, and the lenses are decentered in. So now it's clear that the answer is 1 prism diopter base in. Now you can also remember prism directions by memorizing this chart, which isn't that difficult to memorize. Okay, I divided up all this information on Prism into 2 videos because otherwise it's just so long, it's overwhelming. So that's the end of part 1. Thanks for watching.